Okay, now we should have some sound, right? Okay, again, deadline's approaching for theme 2 of the course. The deadline for the assignment was postponed from Thursday to Friday at 23:55. So you have a few more hours at least for that. Anyway, the first session we talked more about requirements modeling using use cases. The second session we talked about modeling in general and modeling dynamic behavior using state machines, for example. And the let's say theoretical part for today will be about modeling structure, the final task in the assignment. For the assignment, you will be modeling structure after you have implemented. So you will basically take a look at the structure you got. You don't need to refine it or do anything about it. Just present it as it is. In later iterations, you may refine it and change it. You don't need to update this diagram for that purpose. Maybe you have other diagrams you need to do for the final iterations, but not for this task. So as the deadline is approaching, I've also gotten a few submissions from students that we will take a look at, mostly about use case diagrams, a few use cases we will look at, and also a few state machines, at least one, I think. So we will find some common problems that you can maybe recognize in your own work, and then, of course, try to avoid. Sounds good? Feel free to ask any questions also, of course, during this part. All right, let's get started. Present. So today we will talk about structure, as I said. Delicious spaghetti, nice to eat, but don't let your code or structure become spaghetti code or spaghetti structure, where everything is dependent on everything else. Life becomes much harder as a developer. And to take a step back, in kind of like the early days of programming, coding, we could write functions, and just as nowadays all functions rely on some kind of a correct state, some kind of a correct interpretation of data variables that we want this function to use, and output some return value of something. And in the early days, we basically had a global memory to work with. So if I wanted to send some argument, All right, let's hope that these batteries work better. So, yeah, I think it's should be okay now. Great. I don't know where you kind of like dropped off, but the general idea here was that in the early days of software development, we kind of like could just use global memory, and to pass arguments or variables to our function that needed to compute something, we must put the correct data at the correct addresses in memory, so that this function then can read this data. And you can just imagine the mess of things when you have a lot of functions that read a little bit different places in this global memory. You don't really have any great understanding of what function is calling which other function, and what places in memory are taken or not. So if you overwrite a place with some data, behavior of this program will become quite unpredictable. So working with global memory was very hard, and a lot of effort needed to be put into figuring out problems and figuring out how to divide this global memory into parts that the different functions could work with reliably. This was, of course, not very productive. So instead of just working with global memory, we worked with global variables instead. So we dedicated some of the memory to global variables, and the functions could read these global variables, and life is much better, at least to some degree. However, if one function changes a global variable, it can affect the behavior of some other function in some other part of the program, and it's still pretty messy. You don't really know what happens in the program at any point, because all of these global variables can change independently. So as languages has progressed, we have different ways of increasing kind of like the encapsulation of the memory the functions work with, the functionality of our program work with. We have, for example, static variables in classes or modules. We have class variables, object variables, attributes, fields, properties in JavaScript, right? We can have arguments and return values to functions. That's, of course, a big upside and a big improvement to setting some global memory state. And we can have local variables in our functions used for intermediate computations, and really not need to worry about someone else being there and fiddling on these variables. So we have tried to kind of like get a higher degree of structure by using programming languages and finding ways to manage the state of different functions by using program language functionality. Functions also, of course, rely on other functions, and things have a tendency to become quite entangled, even though we have all these techniques at our disposal. So if we don't have any structure or have any idea of how to structure our program, everything has a tendency to become dependent on everything else. And this makes life very hard as a developer, because you cannot really understand the program. You cannot understand a function without understanding the program as a whole. To understand this function, I need to understand every other function in this system. And this limits our ability to build large systems. So with better or with good structure, it's easier to do planning. We can, for example, get a better understanding in what order we should implement things. Because if we have a functionality that's not dependent on any other functionality, that's a good starting point for us. because this is something that we can start working on without having to worry about other things. It's easier to estimate how long things will take. If we have a functionality that's highly dependent on other things, then it's probably more complicated to implement, understand, test, debug, and so on and so forth. It's easier to do cooperation and parallel work because we can divide the functionality items into different teams or different programmers. They can work in parallel, and with good structure, things will hopefully at least be easy to integrate. Maintenance becomes easier because we can know the consequences of a change much easier, and changes hopefully does not ripple through every part of the system. So in a spaghetti situation, if I change the functionality somewhere, there is a high probability that everything needs to be retested, and I need to think about every other function in the system because everything is dependent on everything else. If we have a good structure, changes will be as local as possible and don't affect things on the other side of the system, at least not in an unpredictable way. It's easier to reuse. We can find the parts that are hopefully easy to copy from the system, and I put copy in quotation marks here because, well, copy-paste is one type of reuse, but not the only type of reuse. But if we know what parts of the code base are largely independent of other parts, we can easily take those parts and put them in a library or put them in some other reusable thing, because they are not dependent on the rest of the system. If we have some part we want to reuse, we know the dependence that it has. We can also know how much effort it would be to reuse this part, because we need to cut all those dependencies away. It's possibly easier to change, or at least know what parts are easy to change. So we can, for example, change the user interface to some other neat library if we have few dependencies going on to the user interface. Right, so structure is good. And as you may have noticed, I talked a little bit about this dependency thing. And if we're talking UML right now, a dependency is a basic relation between the parts of the system where when one part is dependent on the other. And it looks something like this. So basically this is a UML class diagram, and that's also what we will be using in the assignment, even though class diagrams can be used to model other things than explicitly object-oriented systems. You can think of these boxes as more or less any structural part that you would like to model. It can be a file that, for example, we will use in the assignment. So each of these boxes represent some part of the system, and one part is dependent on another part, and we show that visually with this dashed line and an open arrowhead. So the left box is dependent on the right box here. And to think about it easily, we can think about it like the first box cannot function without the code in the second box. So if we would, for example, like to reuse the first stuff in the first box, we need to either try to remove this dependency, or we need to take the other box also in this reuse situation. Okay? So, talking about dependencies, we can think about explicit dependencies. And explicit dependencies are, for example, function calls. So inside the code of the first box, we have some function calls that are implemented in the second box. Not strange, right? Maybe there is some kind of a variable in the second box that the first box need to read. There is some data there that we need to access and get. So then we have a dependency. We can have inheritance also. Examples of explicit dependencies. So these are dependencies that we can easily see in the code. So we see if there is a function call. We can see if we read a property. We can see if we do some inheritance or something else. In some languages, this is really, really explicit. For example, in Java, we have words in the language for when we inherit. We have extends and implements, for example. So when you write something in Java, we are very explicit on what type of dependency we are actually using. So explicit dependencies, the thing that you can kind of like express in the programming language easily. If you know Java and other languages, they compile. So you run a little program over the source code and you get something else out of it that's easier to maybe execute. And during this compilation, all these explicit dependencies are evaluated. So the compiler will make sure that these dependencies exist and that they are valid. So if you try to compile the first box without having the second box, the compiler will say, I don't know what to do with this dependency. It's not there. I will not compile. So we can use tools to kind of like know if these dependencies are correct or not. And that's a good thing, right? Because if the dependency should be there, it's not there, it's missing, we will not really like to ship this system to our end users because they are not working. Implicit dependencies, on the other hand, are dependencies that do exist, but it's more on a level that stuff in the first box need to match some other stuff in the second box. And these types of dependencies are not easily expressible in the implementation. So maybe the variable in the second box is some kind of a list or array of something, and the first box needs this list to be sorted. This is kind of like a dependency that we can know that we need a dependency to this variable, but it's come on. It's it's quite hard to express the property that it needs to be sorted easily in the programming language itself, in most programming languages at least. So sometimes you have these implicit dependencies, and those are maybe even more important to show in a model. So if we have such a dependency, we should show that in a model, and we should make this property that it needs to be sorted really visible in this model, because it's not easy to express this in the programming language. One big source of implicit dependencies are also poor implementation. This is something that I come across in student code, of course, because most students are kind of like beginner programmers, and it's easy to take little shortcuts that you think are worth it, or maybe are worth it during the tight deadline. But in the long run, you create all these implicit dependencies that are not easy to spot, and when you then try to extend this program, you don't really understand why it's not working, why it's hard to reuse, why it's hard to change. it's often because you have a lot of implicit dependencies between your parts of the system. One big thing is hard-coded constants. So maybe there is a constant in the second box here, and the first box use the same constant, and these two constants need to match in some way. And if we change the value of the constant in the second box, we need to manually remember to change it in the first box also. Typical example is if the second box, for example, presents a menu with menu choices. Maybe we use Q, press, it says output some string to the user, press Q to quit or something like that, right? The first box then handles kind of like the behavior, what should happen. So it asks the second box to, all right, present the menu and give me the what the user actually typed. And then it has a switch statements, an if statement or something like that. And that says if return value or menu choice equals, and then you have the hard-coded character Q, and then you do something. So, for example, if we later change the language, we make it a Swedish menu instead. So we change the menu output to something with the word avsluta or end or something like that instead. We decide that we need another letter. We change that in the menu output, and we ship our system. Everything is fine. It compiles all right if it's a Java system, no problem. But it won't work because the menu says that you should press A, but the code in the first box here reacts on the letter Q. So we have a dependency, an implicit hidden dependency between these two parts now. And that we need to kind of like remember manually to, oh, I changed the menu, now I need to change this other part also. And of course, you should not use these hard-coded character constants or integer constants or strings in your system because it will become very sensitive to changes. And there are, of course, ways to do a better implementation to avoid these situations at all. Another thing that I see sometimes are, well, this function, it has a lot of arguments of kind of like the same type. So instead of, for example, we could maybe imagine a registration function. You want to register a user, and you send in a username and an email address and a password and maybe other things also. All are strings. So instead of sending them as arguments to this function, it becomes quite long and tedious to work with. You decide to send in an array instead with the user data or something like that. And in this array, you put the username, and then you put the password, and then you put the email address, and so on and so forth. And when you read this data, you index this array with 0, 1, 2, 3, and so on and so forth. And this basically means that everyone that calls this function needs to know what order to send the data in. If the data is switched in some way, behavior will kind of like be unknown. So we have a hidden dependency on the order of stuff in this data array. And that's not a good thing. So try to make all your... I'm ranting too much. Try to make all your dependencies as explicit as possible, and really make an effort to document anything that you cannot make explicit in the implementation. You need to document it really well, because someone needs to remember that implicit dependency and fix that manual and make sure that it's not violated. So in the UML, we have actually then looked at the dependency relation, and the dependency relation is kind of like a catch-all type of relation. We can always use the dependency. It's kind of like the basic type of relation that we can have. But we can also think about dependencies in slightly more refined ways. And if we look at actually the I've already used the dependency relationship in, for example, the use case diagram. So, dashed arrow, open file, arrowhead. So actually the use case diagram is a type of class diagram. If you look at the UML meta model, you will see an inheritance from use case diagram to class diagram. So you have already kind of like encountered a static class diagram that use dependencies. But it doesn't look like boxes, it looks like use cases with ellipses instead. Same problem as last time, right? Oh. So dependency, you can always fall back to dependency, and as you maybe saw in the use case diagram, we can put a little text at the dependency to show more what it's about. We had includes, for example, in the use case diagram. We can have extends in the use case diagram also. One common type of dependency you will see in class diagrams are create. So one part creates the other part. One class creates objects of another type, for example. Then you can have a dependency, and you can put create as that little text to show that this is the meaning of this dependency. Another quite common type of relationship between parts is the association. And this basically means that, well, I in some form one part contains data defined in another part. From object orientation, one class has fields, properties of some other part. For example, we may think that we have a circle class that can output itself on the screen. This circle needs two types of colors. It needs a color for the border, and it needs a color for the fill. So it kind of like contains two color variables. This then becomes two associations to some other part that's called color. Right? And we use this role name that we put on the association to show that, well, this color is the border color. This color is the fill color. So in this circle class, we have a property, a field, something that implements this association. We have a variable with the type color. The role name will be fill color and border color, respectively. So think about the role name as in what way is this type class part used in the other part. Often, however, we see that kind of like the type name is repeated in the role name. We often just, oh, person has a person number, so I put person number and use the same name for the property or the field as the type itself is. But try to find a good role name. In what way is this type actually used? And this, of course, becomes more important when you have multiple associations between the same types. Then you need to think about this more. We can also specify a multiplicity. So a common thing is that one object contains a lot of other objects, a list of objects, an array of objects, or things like that. And we can use a multiplicity to show this. And a common multiplicity is, of course, 1. That's often not explicitly stated. But the star is also common. It means 0 or many as needed. We can also specify intervals, for example, 0 to 5. So we can express stuff in these associations in different ways. If you Google kind of like UML class diagram, you will see often see kind of like these two variations of the association called aggregation and composition. I would actually not recommend that you use them. They only more or less add confusion nowadays. But you can think of them as normal associations, actually. They are good to know, especially maybe composition, if we do domain modeling. But they do have a use if the intended implementation language for our structure is not garbage collected. So if we need to remember what memory is used and what objects actually own other objects and should destroy other objects when they are destroyed, as opposed to just borrowing objects when they are owned by someone else, it's important to know this. Modern programming languages that are not low level have garbage collection, and I doubt that you have managed your own memory, as so far at least. But for example, C++ is a common language where you need to manage the memory on your own. And then it can be important to show explicitly who actually owns objects. And we can think about composition and aggregation. Like in aggregation, we can think about a car that aggregates a number of components, for example, the wheels. But we can change these wheels independently. We can remove them from the car. When we destroy the car, we can remove the wheels and use them in some other car, right? Composition, we can think about that your hand is composed out of fingers, and we cannot easily remove the fingers and reuse them in some other context. But rather, when the hand dies, the finger dies also. So this is a little way to think about aggregation and composition. But in the implementation languages that you face, everything is more or less, you can think about it as common associations. So if you see diagrams with these diamonds, don't be scared. You can think about them as associations, really. We also have inheritance, common relationship, especially in object-oriented systems. We inherit something. We can use inheritance also in the use case diagram between actors. So if we have one actor that can do everything another actor can, it can become quite messy to draw all the arrows the same way. We can think like we have a customer actor and we have a VIP customer. The VIP customer can do everything the customer can do, but then some. And then we can inherit from the customer instead. So we don't need to repeat all these arrows for the customer in the VIP customer. Depending on implementation language, inheritance can be more or less usable also in structural modeling of the system itself. We also have realization. So if you can specify some parts of the systems as interfaces, some kind of a specification or contract, what needs to be there, we can say that different parts can fulfill this realization, fulfill this interface, and we show that with this realization arrow. So inheritance is a straight line with a closed arrowhead. Realization is dashed line with the closed arrowhead. Dependency is the dashed line with the open arrowhead. The most serious mistake is if you kind of like mix realization and dependency, because then the diagram would mean quite a different thing, and that's a mistake we don't really want to do. If we have something that with a role name and a multiplicity, we can probably guess that it's association, no matter what the notation is actually saying. But for realization and dependency, it can be hard to understand what's going on. So try to remember these. You will need to know them for 1DV 607, and if you can do that, you basically will pass the theoretical part of that course. Is my guess, at least. For the assignment, dependency is enough. We probably have a number of different backgrounds regarding language in the course. I know there's a bunch of Java people, but there's also a bunch of JavaScript people, and Java is, well, maybe more object-oriented than JavaScript, depending on how you choose to use the JavaScript. So dependency is fine to use in this assignment for everything. If you would like to do more refined relationships, feel free to do so. We will stay at the file level of things, so the parts that we are talking about in the assignment are basically your source code files. So when you have implemented, look through your source code files and map them out on a diagram. Put every dependency that you can find in them, explicit or implicit, on this diagram, and you will be fine. Finally, some do's and don'ts, very general advice regarding structure. And as I said, the first thing is to try to use as explicit dependencies as possible. Try to express your dependencies in the code so that you can find them easily, either via some kind of a compiler or unit testing or stuff like that. As soon as you have a dependency, try to make it explicit. If you cannot do that, in some ways it can be really hard, then you need to document it thoroughly. I think maybe the best way is to put something in the source code file that says that if you change this, remember to take a look at this other part also. Then it becomes really hard to miss it when you implement. Avoid circular dependencies. So circular dependencies are a well, common anti-pattern in most implementations. So part A depends on part B depends on part A. We don't really cannot really work with that. Some implementation languages also cannot compile that type of dependency, depending on language. It becomes much harder to do the planning. For example, we cannot know, should we start with the first part? Well, to do the first part we need to do the second part, and to do the second part we need to do the first part, so we kind of like don't really know where to start. So of course reuse and everything about that becomes much harder also if you have circular dependencies. And sometimes circular dependencies are also between a not direct as this example as I explained. It can be some classes or some parts in this circle. So the circle can be bigger than just two parts. One idea to solve this is to kind of like take a look at the parts and find what's the dependency about. Take all of that implementation and put that in a third part instead. So we remove the part that's this codependency thing and we put that in a third part, and we let the first part and the second part depend on this third part instead. Then we don't have a circle anymore, at least. Maybe we can use an interface if we have a language that supports that. So to build these parts, we should try to put the same type of responsibility in the same type of part. So if we, for example, have an application that works with circles to some degree, we have some calculations that we need to do on circles, like circumference and radius and stuff like that. The area, for example. Well, to make it easy to for someone else to find this functionality and to understand this system, maybe we should put all this circle math in one part, in one file, for example, in one class or whatever we have as our part. So when you are implementing some feature that needs to calculate the area of a circle, well, you can easily guess that, well, it's probably somewhere in this circle file. I can find a function to do this calculation that I need. So try to put the same responsibility in the same part. And when doing this, we should, of course, also try to avoid kind of like surprises. So when you have your area calculation function, you probably should not output the area to the console in the same function. Right? Because when you maybe just need to calculate the area, you don't necessarily want to print it to the console. Okay? So try to avoid surprising stuff in your responsibilities. And this works also kind of like on a higher level. So maybe we have other geometry stuff. We have rectangles, and we have triangles, and we have spheres, and whatnot. Maybe we put all of these in different files. So we have the rectangle math, and the triangle math, and the circle math in different files. And we put all of these files in a common directory called geometry math, or something like that. Becomes easy to an outsider or someone else in the project to, okay, I need to do a geometry math calculation. I should probably look in this geometry math directory and see if the stuff that I need is there. So we can kind of like build small, bigger parts out of smaller parts, but we should try to keep this responsibility as cohesive as possible. So the parts, the responsibility should be kind of like one thing that we think about. And you, of course, decide what your responsibilities are, how you would like to divide these responsibilities. It's up to you to decide. The math example is, of course, simple because it's understandable for everyone. And in real life, responsibility assignment is not that easy always. And some parts of the system are often quite messy and get a lot of responsibility. And some parts are really not worth trying to fight to get them really, really clean. But math stuff is typically quite clean by definition. So that's why I use it as an example. All right. The second thing, it kind of like ties into this responsibility thing. That is that we should try to encapsulate and protect state. So when I do a part in my system, I would like to show only what's needed for the outside. And if I do anything on the inside in the part, that should be protected as possible. If we do object-oriented programming, this is quite easy to do because we have these keywords that we can put on different parts of our part. It's private, protected, and public. So we can show that these are the parts that anyone can use. These are the parts that only my children can use. These are the parts that only I can use. However, it's also quite easy to violate this, for example, just returning a reference to an internal part in a getter. It's very easy to, well, I made the variable private, but then I made a getter that just returns this variable, a reference to this variable. So we can imagine that we have a sorted list that we would like to maintain sorted. Internally in our sorted list part, it's implemented as an array or something. I write my add item to this list. I make sure that it's sorted still. I make different functions. But then I also would like for people to be able to access the items in the list. So I implement the get item property, get item function, and I just return a reference to this array. That basically means that anyone can change this array in any way possible, and the list will not be sorted anymore. Quite a common mistake. So try not to expose internals if you can protect it. And also there should only be one way to do things. So try to make stuff explicit. For example, in this list example that I told you about, I implement this nice add item thing functionality, but I also return the array as it is. So a user of this class does not really know, should I get the list and add items to the list directly, or should I use this add item functionality that's available? I don't know. I will just do what I'm used to doing, and maybe I'm used to working with arrays and lists. So I just get the list and I add to it directly. So offering several ways to do the same thing to people will probably make people do different things in different parts of the system. Also try only to expose kind of like the functionality that one part needs. It should not be exposed to 1,000 functions, but rather the function that this part needs to work with. So some do's and don'ts. But for the assignment, it's only kind of like the necessary part is that the diagram that you make is actually what's implemented in the code. Then the code can be good or bad, of course, and maybe you will see that it's good and bad on this diagram. Hopefully you will see it. Maybe you will make changes to it in later iterations, but right now in the assignment we are more interested that they match. So there should not be any dependencies in the diagram that's not in the code, and there should not be any missing dependencies that's in the code that's not in the diagram. So it's basically this reverse engineering assignment or task. All right. Questions on this structure? Does it seem easy? I think actually if you have explicit dependencies, doing this reverse engineering is quite easy. You only need to be kind of like thorough and really look through your implementation and find every dependency that's there. So it's quite mechanical, non-creative work. Having a good structure is another thing. So being able to think about structure and being able to model structure is creative work that you kind of like need to learn by experience. And this is the focus of the 1DV 607 course. A lot of effort will go into teaching you how to work with structure to get different properties from your system. I would like to be able to change this part easily. How can we achieve that using structure, for example? So the takeaway message here is that you will work with structure every day. I don't think that you necessarily will work with state machines and use case diagrams and maybe not even use cases in your everyday life as programmers, but you will work with structure every day. And every little decision that you make as programmers may affect structure. So it can be good to think about structure and have it in the back of your head. If I add this dependency, how will this affect structure? Will it make reusability worse? Will it make it easier to reuse? If I have to refactor my code, how should I work with that to make dependencies better? How can I make dependencies more explicit? So structure is something that you will affect and will affect you in your everyday lives as programmers. All right. Let's take 15 minutes of a break then. So, and after that break, we will take a look at some student submissions and discuss what's good and what's to be avoided. All right?
Yeah.
right, I think we're back, and for this second part of this session we will take a look at some diagrams and some use cases that have been sent by students, and we will discuss what's maybe not as good in them. Maybe we will sound a little bit overly negative also, but this is more to make a point. So this was a use case diagram that I got sent to me. It's quite big, but I've zoomed in on one part here so you can see that more clearly, and maybe I should share the whole screen like that instead. So do you see anything strange? Anything that you don't think is good in this diagram?
The implementations you have from Implicit.
These?
The black arrows.
The black arrows. These? Yeah. My guess is that this is a... They should probably be dashed, but I think kind of like the layout and the program used here kind of like have put the dashes on top of each other, so they look like a dashed line, but they look like a solid line, but they're really not. That's of course something you need to think about when you do diagrams, that lines can cross and lines can become on top of each other, and if you have bad luck, this will kind of like change your arrow, especially these structural arrows, right? So that's something to watch out for, definitely. Because if the arrow looks like something else, it's hard to interpret the diagram. Right? Something else? Do your use case diagrams look like this? No? What's the difference?
It's supposed to be mixed with the...
Yeah, you're onto something there, right? This seems to be some kind of a mix between a use case diagram and something else. Maybe a state machine or maybe an activity diagram, because we have this true-false thing going on here, and that's not really part of use case diagrams. Another thing I often see are like you have these kind of like circles of kind of like a flow of things. So we'd select some option here and we do something else and we play the level, and then we do something else, and then we kind of like go back to the menu and we can go round and round here. So a use case diagram is not a flow chart. A use case diagram is strictly just the use cases, and if you decide to do some use case modeling, you may include functionality from another use case. It's not like the user flows and goes around between these use cases. So it's not a flow chart, it's not an activity diagram. We have other diagrams to do flow charts and, well, activity diagrams. So that's one thing. Mind the layout, or two things. Mind the layout so that the arrows don't change. Use case diagrams are static diagrams. They are not flow charts. They don't display dynamics at all. They express more or less who can do what in the system. And if we decide to do a little bit of use case modeling, we can split this up into a little bit more fine-grained functionality also. Something else? Something that I think is quite wonky is that we have the same use case. Play this level, play this level. I think it's play this level over there also. So it's the same use case in 3 spots, and that's not supposed to happen. And discussing with the student in this case, he wanted to express that, well, the user can select a category of words and play the level, play the game with this category of words. So, and I think that's a nice feature, a great feature, super duper thing, but it's not a use case in its own. So when you kind of like add something to a use case, in this case it's more or less selecting an option at the beginning of the use case, it does not automatically mean that you need to write a new use case. In this case, I think it's just a step in the main scenario. Nothing really changes in the flow in the game, in the gameplay itself. The remainder of the use case is exactly the same. It's just an additional step in the main scenario. So don't try to model that in your use case diagram. Write it down in the use case text, and that's it. And you should always try to keep the functionality, the detailed functionality in the use cases, and don't put it in the use case diagram, because it will be totally messy. And we will see things here like the same use case in different places. So when you think of something new in a use case, you try to add it first as a step in a scenario. If this step completely alters or majorly changes the rest of the steps in the scenario, maybe you need to write a new scenario for this little change you have. So first try to change the add a step or two. If that's fine, then that's fine. If there are severe changes in coming steps, then maybe you need to write a new scenario in the use case for this feature. And the final thing is that, well, if there are several scenarios tied into this little feature, then maybe you should break that out into a separate use case instead. So if you get a lot of extensions to this new scenario that you have written, then maybe you should put everything like this in a new use case, because having a big fat use case with everything is also not good. So try to keep the use cases you write to this essential business process level. And this basically means that the use case should express something that the actor actually wants to achieve. That's the basic level that we would like to have. So playing the level, I think, is a fine use case. I think it's called play game or something like that in the original diagram. That's something that we would like to do as a user. View the high score list, for example, would be a good use case, something that we would like to do. It would give us something. Show menu, is that a good use case? Would you be happy if you had shown, I've shown the menu 50 times today? Not really, right?
What if other use cases extend them?
Yes, that is then a use case modeling thing.
And will the user have a direct relationship to the extending use cases?
In that case, I don't think that's good. So because the menu is not something that the user would like to achieve. It's more or less a modeling artifact that, well, we have written this part, this scenario, or these steps in multiple use cases. We break them out into this more reusable thing, and we include it or we extend from that.
I was just wondering about the different options, because once the user comes to the stage where the menu is shown, and it's still the player that is navigating.
Yeah, yeah. But this is exactly this. We don't show this as a flow of events. We show it more like what would the user like to do, and then we express that in our use cases, and then maybe we do this use case modeling to break out common parts to avoid duplication and stuff like that. So think about these essential use cases first, the essential business process things, the things that actually fulfill the wants and needs of the actor, and then we can do use case modeling as a byproduct or as a step to facilitate the lives of us as developers. So I think we have another diagram. Oh, another use case diagram. Again, we have some notational things. It should be not these types of arrows, I think. But again, we have this problem of trying to make an activity diagram or something like that out of our use case diagram. And in this case, it's very obvious because we even have this notation from the select notation here from the activity diagram, the choice diamond in two places, and it's quite obviously a flow chart. That's kind of like what's expressed here. So common mistake, flow chart thinking, activity diagram thinking in your use case diagram. So that is to be avoided. Here we have a third use case diagram. What do you think about that? Are yours similar? Actually, I think this is quite good. We have the primary use cases there, that the stuff that the user really wants to do. View high score list is maybe the most notable addition. And for some reason, guess a letter and choose word list language have been broken out from the play game use case. My guess is that these will be really, really small use cases, kind of like 3 steps or something like that. But maybe there is some point in breaking them out like this. And we cannot really tell that until we have taken a look at the text for the play game use case. So maybe there are several scenarios that kind of like use this guess a letter and choose wordless language, and that would motivate having them as these sub-function level use cases. And as you pointed out, we don't have any lines going from gamer to guess a letter or choose wordless language, because that's not the primary functionality that the user would like to do. The user would like to play the game, and in playing the game he will guess a letter and he will choose the wordless language, but it's not the primary business level functionality. You would not be happy if you selected the wordless language 50 times, right? So next thing is a use case. Can take a few seconds to read that and think about if it's good, what's bad, what could be improved. All right, any ideas?
Where do you come from?
Yeah, exactly. There is some kind of a reference to this use case 1 that we don't really have, but I suspect that's kind of like a main menu display. I don't think that it's really a good use case to start with. We could start with the title, inputting new words. I would just say add a new word, for example. Simpler, easier to understand, expresses what this actor wants to do. Gamer wants to add new word. Precondition, the previous use case, which we don't know which it is, was executed without any errors. I don't think that's a good precondition. A precondition should be something that needs to be true for this scenario to be able to execute. In this case, I don't think there is any precondition. So you don't need to add preconditions that are not really there just because we have a precondition label or part of the use case. Postcondition, I think, is okay. I would focus more that this new word has been added and maybe not show this the main menu is displayed as a postcondition. So the main scenario, the user selects the option to input a new word. As the first step is supposed to be a trigger. OK, trigger, I think it would be easier to just state that the user wants to input a new word or add a new word. This will then mean that he will have us do something in a menu or click a checkbox or do whatever. We don't need to express the details there in the requirement. Just that the user should be able to do this. The system prompts the user to input a new word. Probably okay. The user selects a language, Swedish or English. I think there is probably an error here. I guess the system should prompt the user to select a language. Should be step 2. And then we select the language. And for some reason, step number 4 is the user inputs a new word. I think step number 2 should be between 3 and 4. Probably. And 5, the system checks if the word already exists in the language list. Oh, that's fine. 6, the system displays the new word and displays the main menu. OK. So, always look at the trigger. Do I have a good trigger in my main scenario? And it's quite easy to just write user wants to, and then the use case name. Add new word. More or less, that's a good trigger. Then the second thing to think about is this ping pong match between the system and the actor. So every other step should be actor and system. And we have user, that's the actor first, and then the system, and then the user. And step number 4 is still the user, and then system. So that's probably something wonky going on there. And as we could also read from the steps, it's probably something that's missing here. I would probably also write step 5 and 6 as the same step, and not write it as 2 steps. So you don't need to add kind of like a lot of steps because you just want to express something differently. There can be a point in doing it in this case because it seems like the kind of like this validation step number 5 wants to express that explicitly, and that could be a fine thing to do, but try to keep it as a ping pong match. It's a good rule of thumb. Every other step actor, every other step user, system. I also wonder a little bit about this, the user as the actor. Use the real actor name and don't go for anything kind of like just generic like the user. Use the actor name, the primary actor for this use case. Maybe it's has been renamed in the use case diagram. I don't know, but I think we have gamer as the default. So player, gamer, something like that would say a little bit more than just generic user. We can also debate a little bit about usability here. What if I want to add several words, for example? I will be going back to the main menu again. I will select that I want to do this. I will then need to select the language again, and then I can add my new word. So there are a lot of steps for every word I would like to add. So we can improve the usability of this also by taking a look at these steps and imagine how it will be actually used in real life. And maybe we should do some improvements based on that. But the take-home message from this slide is think about the title. Use simple words, express it as something that the actor wants to do. Pre and post conditions. Are they needed? What's the actual pre and post conditions here? The main scenario, start with a trigger, ping pong match between the system and the actor. Right? For the alternative scenarios, I think they are actually quite good in this case. The two obvious ones are at least there. You could argue that this step should be on a new line and be the first step in this, in how to work in this scenario. So a second use case, probably from the same student as we have the same precondition. For this, we have a little bit the same issue maybe, that the title is not super duper good. Could be just register or something like that. Register as user or something like this. Try to use kind of like these active verb phrases and don't be kind of like passive in your titles. Optimally, we have such a good title that we don't need to write the fully dressed use case, because writing fully dressed use cases are quite boring and laborious. So good title that can express everything we want, then that's fine. Maybe we go to another level and write a sentence or a small paragraph for our use case. If that can suffice, that's fine. And in the extreme cases, we do this really detailed requirement for the use cases that really need to be investigated thoroughly. Again, the precondition says kind of like nothing, so I would not have this precondition in this case. Post condition, I think, is totally wrong. The most important thing here is that you get registered. So that should be expressed in the post condition. Think about the post condition as the test condition that you can use, and if the post condition is fulfilled, then the test case is fulfilled and the functionality works as it should. And in this case, it would suffice to just display the main menu and we would be good. And that's not really what we would like to express here. So I think that the user is registered should be the post condition. Again, in the main scenario, in this case, the trigger is missing. There is no trigger at all, so that should be added first. And then we have kind of like this, you input your name, the name is checked, you input your email, the email is checked, the user inputs the password is checked, the user inputs the second time the password, the system checks, and finally then you're registered and you display the main menu. Okay, so what do we think? You can imagine having kind of like a more comprehensive registration form here. Maybe we need to collect the first name and the second name and the address and the phone number and stuff like that. Holy crap, this use case could be 10 pages long. And the only real computation is really done here in step number 9. And what if I would like to enter the email address first? For some reason we decide that, well, it's better usability to enter the email address first. Then we need to go back and rewrite this requirement, because we have kind of like said that this should happen first and this should happen next. So I think it would be better to write the user inputs, the email address, and the password, and the name as one step.
With also specifying what type of information is it?
Yeah, that it's the name and password and stuff like that. You can, if you have a lot of information, it will be really tedious to write that down. And then you can say kind of like user information. And either you can define user information in your use case as being all of these, this data, or you can have a data dictionary on the side that defines this is user information. So you have a point that if there are a lot of informations there, the text will be totally messy to read. So you can kind of like define user information if you would like to use that word as something and use that in the use case instead. In this case, I think it would be fine to just write down email address, password, and so on and so forth directly. And step number 9 would be kind of like the third step. So we have the trigger, we have the user input, and we have the actual registration. So basically 3 steps, maybe 4 in this use case instead of these 10 steps. And they would say exactly the same thing. And then you add the alternative scenarios, and you would then have kind of like step alternative scenario 3.1, invalid character in username, step 3.2, invalid character in email address, and so on and so forth. So you kind of like handle all this validation in the alternative scenarios instead. That would make this way easier to work with, and would also make us freer to explore different types of user interfaces. And that was kind of like one thing that we said, that we wanted our use cases to avoid specifying user interface things. And by specifying sequence, you kind of like specify some aspects of usability and user interface. So if you can avoid specifying the sequence of stuff, that would be an advantage. And in this case, it doesn't really matter if you input the password first or the name first or whatever first. So then maybe we should not express that in the use case either. So if you find yourself writing kind of like these long filling in a form type use cases, try to make them as short and compact as you can. So I think, yeah, finally we have a state machine. So let's take a look at this state machine and think a little bit about it and find some mistakes that have been done here. Okay, do you see anything? I think it starts pretty good. So we have a starting state, that's good, so we know where we can start in this diagram. And we go to some present menu state, and there we can get an event that says start game. Kind of like weird the double arrows there, but that's probably just a mistake, I think. Then we happen to go into state that says play game, and a new word is generated, and we go into state called a new word, and then we wait for input as an action or as an event. So I think here we have some confusion. Basically, there is present menu, I think, is a good state, because we are kind of like we have presented the menu and we are probably waiting for some input in this menu. So we have a state where the system idles more or less, and then we get some indication that we want to start the game, and then we go into something else. However, this play game state does not seem to really do anything. It doesn't wait. It just performs an action and then moves on. And new word also seems a little bit strange. It's more like this is what have been generated by this this play game state. And then we have a really strange event wait for input. So basically, you need to think about your states, and in your case, your states will mostly be states where you are waiting for user input. The system is halted, it does nothing. The user selects something in a menu, you wait for the user to input the character in the word, etc., etc. So these are what you should model as state. In this case, it seems more like the states are actions. So I think both of these play game and a new word states should be one state. And maybe we should name it play game state or whatever. And in this state, we can write down actions, for example, that we should generate a new word. And when we have this state, we more or less wait for input, and the event that happens is that we get a letter pressed, I guess. So that should be the event. When we have this letter pressed, we can do something about it. So we can check if it's a right letter or a wrong letter. And this should be this choice pseudo-state instead. In this diagram, again, the wrong letter and letter correct place is kind of like the guards in this choice pseudo-state. So they are more or less actions to think about. And we can go into different states. I think lost game is a good state, and correct word is probably a good state also, because here you will probably present something for the user and wait for the user to press a key to confirm or something like that, and then move on. So the important thing to think about here is the states that you decide to have should probably be the points where the application waits for user input. The user input is probably your events. So press a letter would be an event. Choosing start game would be an event, and so on and so forth. I also think that come on, you can do it. Uh-oh. Maybe. Oh. Here we go. Sometimes it's also beneficial to add actions. So we talked a little bit about that the last session, that you can add actions to your to your state machines, and that's basically what should the system do. So the system should probably randomly select a new word. The system should display a message to the user that he has lost or won. So you can express what the system should do also in either the states as entry, exit actions, or on the events themselves by adding this kind of like slash and then write down the action to be performed. And I think if we look back here on the this slide from the last session, we can see that, well, this action is to set a variable to 1000. Then we go into the default state, and when any key is pressed here, we decrease this key count, and we have this choice pseudo state that decides that if we go to 0, then we're done. Otherwise, we loop back into the default state. Caps lock is something that we can press as many times as we want in this little keyboard here. So think about the states, separate that from the actions that you would like the system to perform. And also the events are probably inputs from external user. Right? Questions? No questions? Then I assume that everything will be... yeah, you can write the action on the transition arrow, and you can write it with this slash. So you can have the event, in this case any key, and slash the action. And you can be quite, in the actions, you can be quite kind of like this low level if you want to, but you can also kind of like more express what the user sees or what the system presents to the user. It's fine in this little model that we are doing. So you can also add, I think we had a slide like that, kind of like this, if you would like to have actions on your states instead. So maybe you have a state, and every event that can put you into this state, you want to perform the same action. It would be tedious to write this on every transition and every action into this state, and you can put it as an entry action instead.
Does the NDs are performed before the state or after the state?
The entry action is performed when you move into the state. Then the exit action is performed when you exit the state. So, and you can also have stuff that happens internally if you define the event in the state, or you can have some activity that is performed continuously if you want to. Yeah, sure. My guess is that in the assignment these will not be super duper useful actually. Maybe entry if you would like to put the text in the in the state instead of on the transition. It's fine. All right. Anything else? No? If not, I think it's time for lunch. So I'm available on Slack if you want to. There is a... Okay. If you contact me on Slack, first do it in the main channel, because there is often a bigger chance that someone else can respond faster than I can. And also, I don't really have the time to kind of like do overview, take a look at my model and see if it's correct, kind of like stuff. There will be no chance that I can do that for everyone. So those types of more general feedback is, well, will probably not be answered as thoroughly But if you have specific questions like how do I do this, I'm unsure about this part of my model, or how should I write this use case, feel free to contact me on Slack, or do that in the main channel, and then if I'm first, I'm first. Okay? Or come by my office. Okie doke. That's it for now. You will have Daniel next week, and the theme will be about testing. But good luck on the online exam and on the assignment also. Bye-bye. Stop.